Hey there, welcome back to week 5, chapter 3, part 1. We'll call this part 1B. The last video was getting really long, so I decided that it would be better to go ahead and stop that one and start fresh rather than having it be super long. All right, so let's go ahead and head back to our board. Okay. And here we have week 5, chapter 3, part 1B. And this will be kind of a short video. We're going to talk about 2 things in this video. We're going to talk about that are related to each other. And what they are is it's mass percent and percent composition. Okay, so first of all, let's take a look at mass percent. Mass percent is basically the amount of a compound that you have that is the amount of compound you have, it's the amount of one element inside it or another element inside it. So for example, let's say that we were to take water. Okay, now we remember how to take our molar masses, and again, don't forget that even just for the lecture, you want to have this periodic table and you want to have this ion list here in front of you. Okay, and we know that the molar mass for water is twice 1.008 for my hydrogens, plus 15.999 for my oxygens. And that means that water, I'm just doing the math here, plus 15.999, water has a molar mass of 18.015 grams per mole. Now, if I have one mole of water, then 2.016 grams of it is hydrogen and 15.999 grams of it is oxygen, right? And that's from what I have right here, my hydrogens and my oxygen. And of course, when I add these together, I get this molar mass here. Okay, so, well, what's the percent then? So then what I can do is I can find an overall mass percent of each element. So let's say the mass percent of hydrogen then would be the mass of the hydrogen, 2.016, divided by the total, 18.015, and you turn that into a percent. 2.016 divided by 18.015. I usually change that to a percent in my head, but you can multiply it by 100 if you need to on your calculator. And we can have 4 significant figures, which means that we have 11.19% hydrogen. I could do the same thing and say, okay, well then, what's the mass percent of my oxygen? Okay, well then the mass percent of my oxygen would be 15.999 divided by 18.015, and we turn that into a percent. Okay. And what I see here is 88.809%, because I can have 5 significant figures. And I see that in this case, if I round it, well, if I add these together, 88.809 plus 11.19, what I get is 99.999%. 0.999%. But I can only have 4 significant figures, so this rounds to a nice, even, tidy 100%. Okay? And so the mass percents of each element have to add to 100. So you might say, okay, well, but why do I care? Why is that useful? All right, well, why is that useful is that you can use it to determine what kind of a compound you have if you know the mass percent. Okay, so let's go ahead and looking at my notes. Okay, let's go ahead and take a look at another one. Let's say that we know, well, let's take a look at, we'll go ahead and take a look at the one in the slides actually, and that's Fe2O3. Okay, well let's take a quick look at this, and we're just going to imagine a little bit of a review. And here I see this O, so I know that that's O2 minus, and I can see that that matches that 2 there. And I have that 3 here, which means I know that this is Fe3 plus, which means that I know that this compound is iron 3 oxide. I'm going to throw that in frequently throughout the semester because it is just one of those things that is so important to be in your long-term memory for chemistry. Okay, so let's take a look at this iron 3 oxide. And we're going to do kind of a series of questions and problems with it. The first thing we're going to do is we're going to, maybe you're just given the question, what is the mass percent of each element okay? All right, so if this is your question, well, let's take a look at what we do with that then. Step 1 is going to be to find your molar mass. And actually, let's go ahead and say find your molar mass and the masses of each element. Okay, so first of all, let's do iron. Okay, so the iron is number 26, okay, and there are 2 of them. So we have 2 times 55.845 plus our oxygen, and we have 3 of those, and that's 15.999, okay? And usually I would just do the whole thing on my calculator, but I might as well take it in pieces because I'm going to need it in pieces for finding my mass percents. So if I have 55.845 times 2, this becomes 111.69, 5 sig figs, 5 sig figs, excellent. And then I have 3 times 15.999, and I can have 5 significant figures here as well. So I get 47.997, and that's my iron and my oxygen. Okay, now let's take a look. When we add these together, we can only have these 2 places. Okay, so I will add them together all over though, plus, okay, 111.67, oh, 0.69, okay, 111.69 plus 47.997, there we go. Okay, and what I get here is 159.687, but I can only have the 5 significant figures, so this becomes 159.69 grams per mole. Okay, and then I have my iron and my oxygen. So now I'll come to my step 2, and I'll find the mass percent for each one. So the mass percent for my iron is equal to 111.69 divided by 159.69. And we can have 5 significant figures here. So I end up with 69.942%. And the mass percent of my oxygen, okay, well, there's 2 ways to do this. One way is that I could subtract this from 100, and that would work. And the other way is to do it exactly like I did the first part, and that would be 47.997 divided by 159.69. And I'm going to do it this way because adding them for 100 afterwards is a good way to check. Divided by 159.69. All right, and here I can have 5 significant figures again, and I get 30.056. If you've never taught before, it's amazing how often you can say one thing and write another. Okay, so now let's check this. Often it won't be exact because, of course, you have that significant figures in there. So if I take 30.056 and I add it to 69.942, I get 99.998. And that's pretty good. So it's a good check. Okay, so here are my mass percents. Now, there's something more that we could do with that. We could stop and say, okay, well, I'm not going to often have a sample of exactly 159.69 grams. That's high and it's weird, okay? In the lab, I'm more likely to have a sample where I've measured out 4.50 grams of iron 2 oxide, okay? And if this is my sample, I want to know how many grams of iron I have inside of it. So that's kind of a common problem for something like this. And the way then that I would do that is I would take my sample size, 4.5, and multiply it by my percent, 0.69942. Okay. And I can only have 3 significant figures here, so I would find that I have 3.15 grams of iron. In my sample of 4.5 grams, let's look at one more possibility, okay? And let's say that, number 3, let's say now that what I do is I do a reaction and I find that I have 9.78 grams of oxygen. And I want to know afterwards, so I've evolved this 9.78 grams of oxygen, I've separated it from the iron, and I want to know what the mass of my original sample was. Okay, and so then what I would do here is you can use this original equation to determine that. And so what you would do is you would say, okay, well, if I have 9.78 grams of oxygen divided by my total here is going to equal my percent, so 0.30056, okay? And so when I calculate this out, and I'm sorry, I'm running out of room, but the way you would determine this is you would just switch sides here, and so you would say 9.78, and you would divide that by 0.30056, and that's how you would find that your total is, and I can have 3 significant figures, would be 32.5 grams for my overall sample. So those are just some examples of problems that you can do just with mass percent. That will be very common. All right, so now let's take a look at something that comes out of mass percent. And this next topic is percent composition. And percent composition is really important because let's say that you have an unknown and you don't know what it is. One of your first steps is often to put a part of your unknown sample into a mass spectrometer. And so what you can do is you take a little bit of your sample, you know, your overall sample, it's an unknown, you don't know what's in it. You don't know what elements it has, you don't know what your formula is, you just have an unknown. So this might be done often, like for example, it might be done in the lab to see, like a commercial lab, like a research and development lab, to see what did I actually make here. You might do it, though in that case you would probably have an idea of what elements you had, but you might not know what your overall composition was. Another example of that might be if you were working like in a crime lab and you actually have an unknown. You have a substance right here and you don't know what it is. And one of those key tools that you would have for determining that would be a mass spec. Some other tools, infrared, NMR, those are things that you will learn about in organic chemistry if you go on and take organic. But here we're going to look at analyzing that from a mass spectrometer. So a mass spectrometer gives you percentages of elements, okay? And I'm actually going to go ahead and use what I have in the slide for this, just because that's kind of the way, because I didn't prep another one actually. And it's not one of those things that you can just totally make up. You have to spend a little bit of time back engineering it to find out what your percentages are. Okay, so that being said, let's go ahead and take a look at one of them. And again, this is one of those key places where I am going to want to see your work. If you just give me a formula, I'm just going to assume that you looked it up. So I'm going to want to see your work for this because this isn't something that you can actually do without doing math. Okay, so let's take a look at one. I'm going to sort of combine a couple of problems, okay? And we're specifically looking at caffeine. Yes, I told you it's caffeine, which means that you could cheat and look it up, but we're going to show you how to like determine that what you actually have is caffeine. Okay, and this contains carbon, hydrogen, nitrogen, and oxygen. Okay, and let's say that you didn't know what this was. You have a substance and the mass spec told you that this is what you have: carbon, hydrogen, nitrogen, and oxygen. And when you put your sample in, it told you that you have 49.48% carbon. It told you that you have 5.15% hydrogen, that you have 28.87% nitrogen, and that you have 16.5% oxygen. And you think, oh wow, that's great information. Now what do I have? Okay, and there's a whole step-by-step thing for finding that out. Now, I skipped a step. Sorry, I didn't skip a step, I skipped a topic. One of the things that you're going to find with this is you're going to find that what this is that this is going to give you an empirical formula, because it's going to give you a ratio of elements. It's not going to give you your molecular formula. So let's talk about the difference between those two things. An empirical formula is a little bit like a reduced fraction. And I'm going to work down here and then I'll just erase it for doing it. So an empirical formula is a little bit like a reduced fraction. So if your molecular formula were 4/8, then your empirical formula would be 1/2. And that's what I mean by a reduced fraction. So for example, benzene is C6H6, okay? So this is your molecular formula. And what's your empirical formula? Your empirical formula is what you get when you simplify this. So C6H6 could be simplified to C1H1, or more simply just CH. Okay, let's say that you had N2O4, dinitrogen tetroxide. The empirical formula for this would be NO2. Now this is where things get a little dicey. If you look at the empirical formula for benzene here, CH, you absolutely know that this is an empirical formula because CH isn't an actual thing, okay? But then when we look at the empirical formula for N2O4, we get NO2. And this is where things get tricky because N2O4 and NO2 are both legit molecules. So what you would need to do then is you would need to say, okay, well, which one do I have? And the key that you're going to be using for that is the fact that they would have different molar masses. And so you would be able to look for it in terms of something like that. Another example is, let's say that you have C4H6 as a molecular formula, and the empirical formula for that would be C2H3. Okay, so the empirical formula is just this ratio of elements rather than an actual molecular formula. Okay, so it doesn't tell you what it looks like. It only tells you your ratio. For every one carbon, you have one hydrogen. For every one nitrogen here, you have two oxygens here. For every two carbons, you have three hydrogens. But then you would need the molecular formula to say, oh, well, it looks like this, C4H6, or N2O4, or C6H6. Okay. All right, so now let's go ahead and find what we have for our compound up here with these percentages. Our step one, and all this is in the slides and annotations, but our step one is to set our percentages as masses. And that's just because it doesn't matter. Again, remember, we're looking for a ratio. So as long as we keep the ratios correct, then that's all we really need to do. We could take this out of 100 grams or out of 1,000 grams or out of 1 gram. It doesn't matter as long as our ratios stay the same. And so we're going to set it and we're going to say, okay, well, then I have 49.48 grams of carbon and 5.15 grams of hydrogen and 28.87 grams of nitrogen and 16.5 grams of oxygen. Okay, so one big thing here is earlier in the chapter and going forward, we're really going to talk a lot about diatomic gases, but this is one place where we're not going to be looking at diatomic gases. We're only looking at the element by itself. Even though hydrogen, nitrogen, and oxygen don't exist in nature all by themselves, they're always H2, N2, and O2. Here, we're not looking at actual compounds yet. We're just looking at those ratios of elements. So the next step here, our step 2, is to find our number of moles. Number sign, not hashtag. Okay, and we do that just like we learned in the earlier video, where we divide each one by their molar mass. So here we have 49.48 grams carbon. So we'll do a molar mass like this. So you have, from your periodic table, 12.011 grams of carbon per mole, 1.008 grams of hydrogen per mole. Nitrogen is 14.007 grams per mole. And oxygen is 15.999 grams per mole. Okay, and now we're going to go through this and we're going to do all those calculations. So I say 49.48 divided by 12.011. Okay, now I'm going to be doing a lot of rounding here, so it doesn't matter too much that I have all kinds of information. Hydrogen here only has 3 significant figures, so I'm going to round everything to 3 sig figs here. And I will get 4.12 moles of carbon. And the next I have 5.15 divided by 1.008, and I get 5.11. moles of hydrogen. Okay, and now I have 28.87 divided by 14.007, and I get 2.06 moles of nitrogen. And last but not least, I have 16.5 divided by 15.999, or 1.03 moles of oxygen. Now, our step 3 here is to divide by the smallest. And you might say, why? Okay, well, we're dividing by the smallest because what that's going to do is that's going to set our ratios against 1. We need one of these to be against 1 in order to determine an empirical formula. So that means that we divide each one by 1.03 because that's the smallest one that we have here. And what I'm doing is I'm just writing a divided 1.03 for each of them. And here I see that this one will be 1. And I'm going to go ahead and put the oxygen there. So I have 1 oxygen. Now 2.06 moles of nitrogen divided by 1.03 would be 2 moles of nitrogen. Okay, now I can't do this in my head. Well, I probably could, but 5.11 divided by 1.03. Okay, I get 4.96. 4.96 is really close to 5. So if it's really close, you can round it. If it's not really close, you would not round it. So if it was 4.75, you wouldn't round that. If it was 4.5, you definitely wouldn't round that. If it was 4.25, you wouldn't round that either. You might round 5.01 or 4.96. So if it's within like 10%, like the 0.1, then go ahead and round it. If it's farther than 0.1, don't round it. Okay, so here we'll have 5 moles of hydrogen, and I have 4.12 divided by 1.03, and that's actually an even 4, and that's 4 carbons. So these numbers that we have here become our subscripts. So that means that our empirical formula, and the empirical formula, remember, is just the ratio of elements to each other, is C4H5N2O1. And with the numbers that I have here, that's as far as I can get, okay? So now let's take this a step further. And let's say that we know that our empirical formula, and that was the one that I just found, is equal to C4H5N2O1. But I want to know what this actually is, because I don't know if this is my empirical formula or if it's also my molecular formula. If my molecular formula is bigger, I'm not quite sure. So say, okay, well, then how am I going to find that out? And again, these problems, you have to show your work on them, okay? Because if you don't show your work, I'm going to assume that you just looked something up. Okay, so in order to determine a molecular formula from an empirical formula, what you need to do is you need to say, you need a molar mass. So maybe the next thing that they do is they give you that for the molecular formula, and I'll go ahead and change this, empirical formula. Okay, for the molecular formula, let's see that they told you that we have 194.2 grams per mole. You might be like, why is she writing it so weird? And that's so that I can make a table. There we go. All right, now in order to find the molecular formula, first you need to find the molar mass that goes with your empirical formula, okay? So then you say, okay, well, my molar mass for this is going to be 4 carbons. plus 5 hydrogens plus 2 nitrogens plus 1 oxygen. So I get 48.044 for the carbons and 5.04 for the hydrogens and 28.014 for my nitrogens, and then my oxygen is still 15.999. And I add them all up. And what I get here is that I get a molar mass for my empirical formula of 97.097 grams per mole. So in order to find my molecular formula, what I need to do is I need to divide the molecular formula molar mass by the empirical formula molar mass. So I come over here and I say, okay, well, 194.2 divided by 97.097 is approximately 2. Now again, you're looking for an even number here, and you will get one. Okay, now I take this 2 and I multiply it by the subscripts in my empirical formula. So 2 times 4 and 2 times 5 and 2 times 2 and 2 times 1. And what I get then for a molecular formula is C8H10N4O2. And that's the final answer for my molecular formula. All right, that brings us to the end of part 1 of chapter 3. Next week, we'll be doing balanced equations and stoichiometry and limiting reactant stoichiometry and percent yields. All right, good luck. I'll see you in recitation.